So we've got another Lynx 2 here for repair. This is a slightly rarer VLSI version made by Epix, as opposed to the Hayato chip, which is more common. And the customer sent this in, saying if we want to make a YouTube video, we can. And I think we will, because it'll be useful for people. He says, please don't be too savage to the person that did the work. Somebody else has worked on this before. Don't worry, my name's not Voltaire. We don't do that here. So let's get started, and let's get this thing rigged up for basically a quick power test. So if you just jump over to retro6.wiki, go to the power circuit, or even safe boot, whichever you want to do, if you know what to do on this. First step is to bridge the pins here, and it looks like somebody's already done this potentially. As I mentioned, someone's worked on this already, so you can see there's like torn traces on audio, and you can clearly see there's been work. So let's just bridge these two anyway and start from scratch. What this does is this allows us to not have to have a game in when we're testing, so this bypasses the circuit. And if you want to see where that happens, if you go to power circuit, you can see absolutely tons of info here on diagnosing, but this is what we just bypassed. So the U6 chip that handles boot up gets its power pin, its VCC pin, going through the cartridge connector pin 31 and out when a game's inserted to pin 33, which is the output rail, effectively the battery terminal. So by bridging those two pins, we've bypassed the need for a game and powered the U6 chip here. And then one more thing I want to do, because I don't want to have to use the customer's screen and keep inserting and removing this and potentially damage their screen, I always use a donor screen. Now I only have the Hayato screens. Again, if you check the wiki, I've done a lot of reverse engineering on this, but the Hayato screens don't bridge pin 25 and 26 together. And if we take a look at the LCD enable pin, you can see that the Mikey screen bridges pin 25 and 26 together, and the Hayato one we've just shown you doesn't. And the workaround for that is to bridge these two pins on the back. This allows us to use any LCD on this rarer variant, and you can use any LCD on the other variants anyway. So you only need to do this on the Mickey chip variants. So we just bridge them two like that. We should now be able to use our screen. We've got a game in anyway, but we don't need that. But bridging this helps with if the game was, say, dirty and not making good contact. So this is pretty much what I leave in as standard. Those two fixes I leave as a permanent fix. So next up, we'll bypass the entire power circuit in case that's an issue and just see if we can get this console booting. We'll attach a wire to the shield ground, which is the system's ground. So that's bypassing all of this power circuit and go straight to a shield pin. And this is in safe boot. If we carry on with that article, bridge the two, confirm the 5-volt regulator. We're not even going to confirm the regulation yet. We're just going to go with injecting 5 volts. And you basically have to put the black probe on the metal shield, not the battery spring. That's the important part. And inject 5 volts only. So if we were to connect here and inject 9 volts to the battery terminal, we would potentially kill the entire console. And then we want to monitor for the current draw and also, I guess, the screen, see if the screen comes on. Usually you find most of these issues are just the power regulation side. You can see there we've got a backlight, half an amp draw, so that's good. And there you go, we got the game. This is just a slightly dodgy screen I have to push on this corner normally to get that to come back. And there you go, you can see if I just push on this screen here, I get the full screen. This is just my test screen, I know that side's kind of faulty. So we know the console's working in general. So now we know that, we don't really need a screen for now. We can base it on current draw. And this time we are going to now drop back to the battery spring, still keeping 5 volts, that's the important part. And if we inject 5 volts here, you can see the system isn't booted yet. And to boot the system, you want to short TP17 to TP18. And you can see nothing much happens at all. We have like a milliamp. So with that said, let's stop monitoring the current and instead just connect the 5 volts straight up. And instead I'm going to use the oscilloscope. We're going to grab onto the battery ground because the U6 and power up side is on battery ground. And let's focus our attention now on the U6 chip. Again, what we're going to run through now is this power circuit system. So too long didn't read quick tests. We've shorted pins 31 and 33. We've applied 5 volts. Now we want to test U6. So we want to measure U6 pin 14 with a multimeter. to make sure we have power. So just quickly tap on there, you can see we've got 5 volts. So next you want to measure all the voltages of U6. And it's all explained in this article if you want to know, but basically start at normally pin 13, which is the input, which is 5 volts. And when we sync that to ground by touching it to TP17, we should turn the system on. So in the off state at the moment, it should be 5500550. So if we just go down this side, we have 5, 5, 0, 0, 5, 5, and 0, which is what we should expect. And the other side, we should have, starting from the top, 500, 5500. So we have 5, 0, 0, 5, 5, 0, 0. So U6 looks good, which is a good start. Next, we want to test Q8, which is here. And the way we test that is we short pin 13, which is here, which also looks a little bit dicey. But it's obviously working, so we've tested anyway. But pin 13 wants to be shorted to pin 7, which is effectively ground down here. So we short them two together, which is the same as shorting TP17 and 18. That's what we've just done. So if we go on to TP18, which is literally joined to pin 13, just so it's a bit easier to probe. And if we short TP17, which is pin 7, to TP18, we should see it go to ground, which we do, and it stays to ground. Next, we want to check that these pins on the right are 5 volts and zeros, and that the lefts are oscillating, as well as the bottom corner. This will be the buck circuit operating through Q8 on feedback from the Zener diode and resistor. So at the top of here, you can see we've got a solid 5 volts, no oscillation. Ground, ground, 5, 5, ground, ground. So there's no oscillation happening. So we should see this on pin 1. You can see we're not seeing anything like that. We just have 5 volt static. And then all the other oscillations, they're not there. So we keep scrolling down and reading. If you see a non-oscillation, if you see a non-spiked oscillation like this, we don't see that either. So it's not there. So short pin 13 to pin 7, which is ground, that's what we just did. If you see a solid 5 volts, which is what we're seeing, instead of pulsing, then the Q8 transistor must be permanently conducting. This means that the base is always lower than the emitter, which is either the case, or R74 or D13 are bad, which effectively pulls the emitter low. So either Q8's bad, or we have a short, or R74 or D13 are bad. So with that knowledge, we can look around. We have D13 here, we have Q8 here. So if we probe the base, you can see the base is high, not low. And the emitter is high. And the collector is also high. And this shouldn't happen because when the base and the emitter are the same potential, then the collector shouldn't be active, which means there shouldn't be high. So we must have a faulty Q8 transistor based on that. So let's just swap that over. I'll just take one off a donor board and chuck it on here. With a new one on, and plenty of time for that to cool. Don't power the circuit up until you can hold your finger on the place you've worked on without it burning, because otherwise this could be in like a dead short or, you know, a non-functional state, which will make this not work. You could also kill the transistor you've put on. So that's nice and cool now. I'll apply power back to the circuit. And let's do the same test again. Let's just bridge TP17 and 18. Right, now we're seeing 12 milliamps. We didn't see that before. So I'm guessing now. Let's probe pin 1. Right, we have some kind of oscillation there now. So let's just check this again so we can see. So you see the base is 4.4 volts now, whereas the emitter is 4.9. So this is down half a volt, which is then going to pass current and amplify the current from the base out to the collector, which then is effectively pin 1 of U6. And through a very elaborate circuit, all explained in great detail here from my reverse engineering, you'll get a buck converter through oscillations and feedbacks. So if you're interested in how that works, pretty much if you went to the buck converter section and you read from here, the self oscillations explained, the feedback circuit with the pulses for efficiencies explained, and that's really it there. That's your main chunk there, explains how this oscillation works. And if we look now at our pin 1, we are seeing an oscillation, but it's 2.56 and it's like small. It doesn't look like this, which is what we should be seeing. So we've got something, but we certainly don't have it. We don't have the spikes. We don't really have this. That's a bit more amplified. We have a much flatter and consistent visual. So this looks like it's regulating, just regulating wrong. So let's measure. If we go to the top of the article, shows you how to measure output voltage. Importantly, you touch on the shield, not the battery spring, and then measure to effectively the battery is positive for the system's output voltage. And if we now touch on the shield and the battery terminal here, you can see we've got 1.34 volts out. And obviously, input voltage is 5 volts. So with a regulation circuit, it should be 5 volts. And we're getting 1.33. And we at least know the circuit is oscillating to try to power on, because that's why we're seeing this oscillation. If it was flat, we know we haven't got a feedback circuit. So we now need to check in the power circuit section. If we scroll down, we don't see solid. We have a note here. If you see oscillations in pin 1, but lower than expected voltage on output, which is what we do, then see diode D13 could be backwards or faulty. Also Q12 could be faulty. Test with the multimeter in diode mode. So let's just have a glance over those two. And we have Q12 here, which is not looking the best there. I'll probably set that down. But we know, and we have D13 here, which I think actually is on backwards. Yeah, I'm pretty sure that's on backwards. So let's just take that off and I'll show you how to measure these properly. So it's coming off with green to the left. And because these are awkward to measure when they are loose, I'm just going to stand it up on end and just solder it to that solder blob there. So we're still using the circuit in essence. So this isn't going anywhere on the circuit now, it's just being held effectively physically there so we can test with the multimeter. Put the multimeter into diode mode, and in diode mode, when it shorts out, it beeps. For Zener diodes, you can't really test one way, where it's the high breakdown voltage, like the 4.3 volts. But we can test the other way around, which is when the diode is forward biased, and you should get your basic voltage drop, like 0.7. So on the Lynx, the volts drop, you should have ground here, positive here, and you should see a volts drop of 0.7 that way. So that would mean, with our probes, ground here, positive here, we should get a volts drop, and we're not. So that, I'm guessing, is on backwards. So we flip the leads around. Yeah, you can see we get the volts drop that way around. So the Zener end, the breakdown end here, is effectively this end here with the line, which should be going to Q8. So the negative probe, when it beeps with 0.6 volt breakdown, should go to the Q8 side. So that means if we want to test Q8 base there to there, you can see that's the pin. So we know that's the side that the black probe on the diode, when it breaks down voltage, should go to. And you can see it's on backwards there. So if we flip that around, and I'll also just quickly tidy up them pins. I think this was a lead-free solder as well. Seems a lot higher melting point. Make sure we rotate this around. Now the diode's on again. Really important to just let it cool down. That's had enough time now. I can touch the board, put 5 volts on, and I can see straight away the current draws 160 milliamps, so I'm pretty confident that's just booted. Let's now check on pin 1, and there we go. You can now see clearly the exact voltage wave that we get if we go to the known working wave here. We basically get that exact same thing. And then the other pins should oscillate. You can see pin 2 oscillates correctly, pin 3 does, so effectively it goes high, high, oscillation-wise, then low, low. So very similar to just static high, static low, but it's pulsing and oscillating, which is the buck converter running. Yep, so those are all good. Let's chuck our multimeter into diode mode. Black lead on the shield, red on the input, and you can see we're regulating to 4.7 volts, and we're at 5 on the bench. So next is to check it really is regulating. I'm going to increase the input voltage. We're now at 5.4 volts. And the output's still 4.7. You can see input is 5.4. So it looks like we're regulating. I'm going to bump the voltage now up to 9 volts. So you can see we have 9 volts on the input. And if I move the black probe to the shield, we have 4.7 on the output. So I presume this now is a working system. So let's just unplug all the leads. Let me just set that Q12 down as well. When you're doing something with a heavy trace as well, don't go over the component first, warm the board near it first, like this. And then once it's had a bit of warm, then go onto the component to set it down. That's nice and flat now. We don't need this wire on for now. And let's just get the customer's front board. Now I'm fairly confident this is working. We have a game in. And this will test now the customer's screen. As well as we might as well test the entire circuit with the button ribbon to see if everything powers up from pressing the button ribbon. So that's everything connected. We'll just connect to the battery. And we have 9 volts on the input. Check this is cool enough. Not quite yet. And I can't stress enough, whenever you've worked on components, let them cool before you power things back up. Rushing this can blow any part of the circuit as well as components that you've just put on. So just take your time when you're doing this. We have the 9 volts on, and let's see if the on button works. And no, his on button doesn't work. So let's just short pin 6 and 7 ourselves, which is the same as shorting TP 17 to 18 for the most part. And you can see when we do that, the current draw has gone up. And there's the game. You can barely see it. And there's the game loaded. So the screen's got, the 3 sections are quite a bit different, but you can't do much about that. That's the screen. You can always upgrade this to a clean screen if you like. So we now have powering up, but there's a few more issues. So let's fix that issue with the ribbon. We sell new ribbons, but normally, before you buy a new ribbon, you can just get a pair of scissors and trim off the end that's all worn here to expose some fresh carbon. So we just take the scissors and trim off all the used carbon, and then this saves a bit of money for the customer not having to buy new ribbons. That's that back in, and let's just do another test if that now turns on with the actual ribbon in there. Hopefully it does. That's on. Yep, and there we go. And now it says insert game, which I presume is just a failed load. Yep, just reinsert the game, and it's going to load, I'm pretty sure. Yeah, so that's the button ribbon fixed. On off works. We'll let it load, just check flip works. Backlight. Backlight on off works. Flip works as well. It's a little bit hard to press, but flip does work. So that's working on the ribbon. And the only thing left is we have no audio. So let's just take the screen out now we're done. And we can see for one, whether that's only just happened with the moving around, but the wire's actually off the speaker. You can also see there's been work done up here and ripped traces and that. So I'll just reflow that into place and reflow the speaker. Just try and clean up this area a little bit, see if we can expose what was here. I don't have another specific version of this Lynx to hand at the minute to check where things go. So it looks like, based on what I can see here, it comes from the speaker it goes a capacitor to ground, through a resistor and back to this chip. So this was hanging off and this cap was over here, not in the right place. So I'm pretty sure what we need to do is connect this resistor. Connect this resistor back up to this pin here. So let's just clean that off. Get all this excess solder out of the way. Chuck a bit of flux on here in a minute if I need to. So there is the resistor that would go straight to the wheel in a moment. And then from the wheel, which is the same as this, to ground. So this pin would want to go to ground. So it will go on the ground pad here. So that restores the cap to ground, and now we've just got to restore the resistor underneath here. I've checked under the wheel and this cap is already tacked to it, so we can just go from there to the resistor. So we have that tacked onto the capacitor, like so. So now we have a solid wire here. The resistor's caught solid, that's on the wheel. Put this back to ground, and make sure this isn't shorting the resistor pad, which it isn't. Let's give that a quick go. So we've got speaker in. Let's just turn on and see if we get audio without really bothering with the game for now. And then if we don't hear audio, we can always chuck the screen in and have a quick double check. No, still no audio. Just check a few speakers. Yep, no audio there. So we take a real quick view at the schematic for now. And we have been measuring on ours. We saw the voltage here. And before that goes through U7, and it effectively comes out of pins 7, 12, 14, and 21 on the Hayato. So it's probably similar on the Mikey chip. Let's just see if we see anything in U7. So you can see U7 is getting audio signals, and they do appear to be coming out. So we know the Mikey chip in this case is passing it through the filters into the U7, out to U7, and this set of resistors here has got the audio on. So you can see right there, there's the audio. So we know that audio is making its way to the bottom of R40, and at this point it should head up to the wheel. I'm pretty sure that goes to that via. So we have one via here, which I believe is this via here. Goes along and up, and that's probably the second one. But it goes to there, up to what I think is R42. So let's just check that. There's the bottom of R42, top of R42. So we're correct there. After that, it goes to this capacitor. So if it goes into wheel and goes into the amp and it's fine, then the amp's probably dead. So I'm guessing U12, which is actually U5 on our board. The amp is probably dead. But let's still check. Let's continue probing all the way. So we have the audio there. We don't even get it to there. So audio makes it there. And doesn't even make it to the capacitor, which is weird. Looks like it does. So is it as simple as we literally have, yep, actually, we have no trace there. If we look at that closely, you can see, I believe that is completely missing. So, tack onto that, reflow that, and then just wiggle the wire. And there's that restored. Now the wheel only has one input and output, so quite clearly it's only a mono setup. They probably pre-mixed the audio here as opposed to it being actual mono, but either way, I think that's the only thing we should have to repair. We've seen it on the scope now going pretty much all the way up to the top, so I can't imagine this not working, and apparently not. So let's just probe now. Do we get the audio going to the capacitor? So we get audio there, and we don't get through the cap. Let's do some basic continuity, that things aren't shorted, which they aren't, which is what's making me think the amp's probably bad, because this literally goes to effectively where we are here, which is into this pin here. So we've come through this cap, and then we should be going to the wheel, and it's actually got another cap, to be honest, so the cap's probably not needed. And then we come through the wheel, and the other side has this cap to ground, which is the one we repaired, and then it should just go straight into pin 7. And to be honest, this isn't that vital, this cap, for getting in the way, but so instead of messing with all that wheel, let's just bypass it all and go to the underside straight to here. Because for whatever reason, I think we'll take that big capacitor off that somebody else has already put on, because maybe that, so just taking that cap off from under there that somebody else had already put on, just in case that's the problem. It's not that vital. It's a filter cap, so let's just keep that out of the way and start fresh. We've got a lead on there now, which we know already works from there, which I believe should be the output afterwards. Ah, yeah, I can actually see the issue. They'd soldered to this pad, not this pad, so that's why that was then shorting to ground. So now we've restored that. I believe it's meant to go through this and out the other side, so I'm pretty sure to go onto this pad, the output, because this is the input. So just go output, back around, and then we'll just do resistor straight to the pin. We can just chuck the 10k resistor back on its pad, and we can solder this enamel wire back to the resistor. So that's the only slight problem when other people have worked on a board. You can't really presume where things are connected to is correct. So even though they looked correct, we were missing a trace here. There was a cap going to the wrong place. There's torn pads. So if you're working on stuff that other people have worked on, some people won't work on them. Others will just charge more. To me, it doesn't make a massive difference. I like to reverse engineer circuits anyway and figure out how they work. So I kind of find the problem naturally from just doing what I'm doing, is looking at the circuit through a scope, finding out what's wrong, finding out what doesn't match, and then fixing it. So now I'm fairly confident we should finally have audio. So let's just leave the screen off again and just go for a plain boot. Volume up, power on, turn on circuit. And I'd be quite surprised if this doesn't work. Now, if it doesn't, then I reckon, like I say, the amp's dead, but we haven't yet seen the audio go into the amp, so that's not part of the equation yet. So still nothing. So let's just check if my work is correct. We're seeing audio there, but it doesn't seem to ever make it to... There's the wheel. So it's making it to the wheel. Coming off this side, and there you go. It's actually, once it comes off there, it dies, which is this pad here. So we're getting it one side of the wheel, and it's never coming out the other side. Like literally not coming out the other side of this wheel. So this wheel looks like it's the problem. So how do we do that? Instead of replacing the wheel, I don't have one for now. We'll just bypass the wheel and it'll be full volume. So to do that, we can simply solder to where I said I was. So to do that, let's just move this wire from the output, which doesn't seem to be doing anything, which is a sign that the wheel has broken inside. It's just a potentiometer, so it's obviously broken inside, which is good news in a way, because then you just have to replace the wheel and move that wire over. I'm just going to chuck that back down on the pad. And I might as well put it in the right way so it looks neat. And now that's on, let's do about the 50th test. I'm still confident now we're definitely going to get audio. So here we go again. TP17 to 18. Wheel now does nothing, so you can ignore the wheel. And I'm pretty sure now we should get audio coming out, just the volume wheel won't do anything. And there we go. And then obviously, like I said, volume wheel doesn't do anything. So that's that repaired, I think, as far as we should go. The customer can swap this wheel if they have a donor, or they can pay us for taking it off a donor board. But that's a simple fix now, and then that console should be fully up and running. So hopefully that's useful to you guys. If you want any more information, just head over to retro6.wiki, or our Discord channel, or our YouTube channel. They're all linked here. And if you have any troublesome repairs you can't fix and you want to send them in for me to do a repair video on, just let me know. That's it for this one, guys, and I'll catch you in the next.